This is the second hour of Physics 1C for November 15th. We're going to continue on showing you some other types of Faraday's Law problems that you'll see show up in your homework. And here's another one. So in this problem, we have a current I that flows through a wire here. There is a rectangular shaped loop, although it's curved on the edges. We're going to treat it as if it's actually a rectangle. And this rectangle has dimensions of L and I guess b minus a or something like that, because b is the distance from here to here, a is the distance from here to here. And there's some other things drawn in here. We'll talk about what they are. Let's read the problem now. It thinks this is a this is a one dot problem. This is funny to me. They usually put 1, 2, or 3 dots next to the problem based on difficulty. This one is not a one dot problem. This is pretty hard. All right, anyway, so it says the current in the long straight wire AB shown is upward and is increasing, that's important of course, steadily at a rate of di dt. A. At an instant when the current is I, what are the magnitude and direction of the magnetic fields at a distance r, so here's r, to the right of the wire? So part A, what is the magnetic field created by our wire here? Well, it is a long, straight wire, and we know that... Oh, is this one of the actual homework problems? Did I assign this one as a homework problem too? Kyan? Is that what you're saying? That this is going to be equal to mu naught times I divided by 2 pi r. It's okay if I did. There's nothing wrong with going through super similar. Well, that's why we're doing it, is because the goal is to do something that's kind of the same, but then when you go to do it on your homework, it has to be a little different. And I know that there are probably tons of problems on your homework that we didn't do anything in class that's like that's kind of just what happens in physics classes. I can't do every single type of problem, but when I can, I will do as many as I can. And I know a lot of really good Faraday's Law problems, and it's one of those that has a lot of variation in the types of problems you get, so we just do a bunch of them. Anyway, this is what our magnetic field's going to be. We also want to find the direction, so to do that, think for a second, what's the direction of the magnetic field inside of here due to this long current carrying wire? Should I draw into the page or out of the page for the magnetic field? Right here. Is it into the page? Into the page, that's right. So what I'm going to do is I'm going to say the magnetic field, it gets weaker as we move to the right. So I'm going to say that we'll just draw smaller x's to indicate the fact that the field is a little bit weaker on the right side than it is on the left side, but we know that the magnetic field is pointing into the page. And this is the magnetic field, again, created by this wire here. Okay? All right. So part B. Part B says, what is the flux d phi b through the narrow shaded strip? I don't know if we've done anything like this yet in this class. Maybe we have, not sure. But we can find the flux by doing b dot dA. Okay. And dA is going to be the area of this little shaded strip right here. Okay. You can see that the thickness is defined as dr. That's the thickness here, is going to be dr. The length is L, so I would argue that our area in this case, dA, is going to be equal to the length L times dr. And then we can put that together here to find the infinitesimal flux flowing through that strip right there. So that's going to be B times L times dr. Basically just magnetic field times area. Part C, find the total flux through the loop. In order to find the total flux, all we have to do, we'll write the full version. We're going to find the surface integral of b dot dA. We just figured out that b dot dA is just equal to BLDR, right? So we can put all that together. So we're going to have BLDR. And now, since we're only using one variable, we can get rid of one of these. We've effectively already integrated in that direction, and that's where the L comes from. we're going to be integrating from the left side of the loop to the right side of the loop. On the left side of the loop, a is equal to r. So we have a here. And on the right side of the loop, the full distance here is b. So we're going to be integrating from a to b of BL dr. But we know what the magnetic field is. The length is constant. I'll pull that out. The magnetic field is given from above as mu naught times I divided by 2 pi r. And we're integrating from a to b. And then dr is the thing I left off. We can, of course, pull out all this stuff to where we're just doing an integral from a to b of dr over r, which we know to be natural log. So we're going to get L mu naught I divided by 2 pi times the natural log of b over a. Again, if you don't remember, the integral of 1 over x dx is the natural log of x. And I know in your math class there's probably something like an absolute value sign on this. In this particular section, b and a are just positive quantities, so I'm not drawing the absolute value on there. But that is our flux, phi b. We're going to get values later that we'll plug in, but for now that's all we have. Let's check the units of this. Flux should have units of Tesla meters squared. And the units here are meters times mu naught, which was Tesla over meter time amp. And then current has units of amps. Is that right? Mu naught? Oh, we're going to go back to the previous problem where we used this. Tesla times meter over amp. Did I mess it up again? I did. I messed it up. It's Tesla's times meters over amps, which means the amps cancel and you get units of Tesla time meter squared, which are the units you want for flux, because flux is B times A. A Tesla times a meter squared I think is also equal to a Weber, but I don't really use that very often. I don't like introducing extra units when we don't really need to. I think there's already too many derived units. Regardless, here we go. That's our flux. Any questions about that? Come over here for part D. Part D says, what is the induced EMF in the loop? Well, according to Faraday's law, we know the induced EMF should be equal to negative rate of change of flux. So in our case, that's going to be ddt of that thing over there on the right. So of all of the things in our equation here, I is the only thing that's changing. So I'm just going to write this as L mu naught over 2 pi natural log of b over a times di dt. So basically, I'm just using that operation for the derivative on all of this stuff here in the flux, but L mu naught 2 pi and log b over a are all constants. I is the only thing that's changing. We're told that the current is increasing at a rate di dt. So that is what our EMF is going to be. And then finally, evaluate the numerical value of the induced EMF if A is equal to 12 centimeters, blah, 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 blah. All these things, right? So given those values, we're going to get that the induced EMF is equal to negative, all right, L is 24.24 meters, mu naught 4 pi times 10 to the minus 7 Tesla meter over amp, multiplied by the natural log of b over a, so 36 divided by 12. It's a ratio, we don't need to put units on that. Divide a whole thing by just 2 pi in the denominator, and then multiply by di dt, which they're saying is 9.6 amps per second. And we're going to get a lot of natural logs today. I was using natural log a lot in my 1B class this morning too. 0.24 times 4 times pi times... Oops. So that's going to be the natural log of 3. I get an EMF of 5 times 10 to the negative 7. What do you all think of that? Does that sound right? And the units for this should be volts. We can check the units on this too. So that is our induced EMF. There is a negative sign on it. The negative sign is not super important. It just indicates direction. It indicates that the induced EMF in this case should be opposite the direction of this current, right? For me, the easiest way to say that, I don't even need to use like Lenz's law or anything, think about it. I just know that the current here cannot be going in the same direction as the current here, right? That has to be the case. So we're going to say that the induced current is this way, and it goes around this way. That is our induced current. And of course, if you check, such a current would produce a magnetic field that points out of the page, which is opposite to the external magnetic field. There we go. Like I said, I like to think of it as if I is this way, right? The external field is this way, then our induced current over here has to be going the other way because the external field is increasing. If this was a negative number here, then the current would flow in the same direction. That's how I interpret the negative sign, at least. You know, I don't think that's an easy problem, but it is relatively short. You all have a problem in your lab manual that's basically the exact same problem, except that the current isn't changing, and instead, the way that you're inducing an EMF is by taking the loop, and it's being moved to the right with a constant speed. So you'll see that show up in your lab manual. The derivation is actually very similar up to this point. So basically, part A, part B, and part C are going to be basically the same. When you get to part D, now the change in flux is produced by the moving field, or sorry, the moving loop, and it'll just kind of slightly change the way you do it. But you all figure it out. You're clever. You can check the units here too. This one's pretty easy. The amps here, those cancel. You have Tesla times meters squared divided by seconds, and that's exactly what a volt is. Okay, so the next topic is related to Lenz's law. It's related to this problem right here, but we're gonna have to talk about it a little bit first. And that is induced electric fields. So we've talked about induced EMFs. We've talked about induced currents, which are obviously produced because if you have an EMF, you're going to get electric current. Next, we want to talk about inducing electric fields. We've also talked about induced magnetic fields, haven't we, actually? So we've talked about the induction of EMF, the induction of current, the induction of magnetic fields, right? Which basically tells us all of it comes from Faraday's law, which tells us that anytime magnetic flux changes, you're going to get an induced EMF. If you have a wire that has a small amount of resistance to it, you're going to get an induced current, and that induced current is then going to produce an induced magnetic field. But what we're going to find now is that inside of these wires that are having these induced currents, there's actually going to be an induced electric field within the wires as well. So your book has a nice picture of this. I'm going to do my best to draw my own picture because I just have found, I think that it's easier to understand what's going on if I don't just show you a picture, as long as I can draw it in a somewhat reasonable way. So suppose that I have an air core solenoid where one end is right here. So this is going to be an end cap that has an area A, and I'm going to have a solenoid, so I need to have a tube around which I can wrap some wires. So let's draw a little tube here. Think of it just as like the inside of a paper towel thing, where it's like the paper towel holder, I guess you'd call it. Something like that, just a cylinder. And wrapped around this, we're gonna have a wire. So we're gonna have a wire that wraps around this way, up to here, then it comes out the back again, and then it wraps around like this, comes out the back again, and wraps around like this, and we'll just, one long wire that's wrapped all the way around. There we go. And then it will come back up the outside here. So we're gonna have current that's flowing in this, and we're gonna say that that current is changing with time. So we've got current flowing through here. Let's just call it, we'll call it I. And we'll also say that it's changing. So it has a first derivative that's not 0. Okay, we'll say the current flows in this way and back out this way. So that means that across these little pieces here, it's flowing like this. And that means that the direction of the magnetic field produced by such an object like this, I believe, is going to go to the right. Let's use this. Magnetic field here should go this way. You should kind of verify for yourself that that's the case. Because if you wrap your fingers like in the direction the current's flowing like this, it's like coming over the top of this object, your thumb points up and to the right. So that's the magnetic field of the solenoid, right? Now, around this, we're going to put another ring here. Let's use yellow. Now, how do I make it look like this is around this, but not look weird? I guess that's fine. Maybe I'll make it a little bit smaller. And we'll erase the part that goes behind. So we put a wire around here. I don't know if I want to make this like fatter, or I guess I want to make it like proportionally look similar to that A on the end or something. I don't know. I'm not good with this kind of stuff. Let's just erase the part that goes behind. So this piece here. Just erase that and then draw our wire back in so it's still connected. Okay. So we place this ring here. And also, we are going to, at the top right here, put an ammeter. So we'll stick an ammeter inside of our ring, like that. And now we're going to, so this is really similar to the first problem we did, right? We've got a solenoid, and we place another loop around that solenoid, and we also, on our loop, we put an ammeter, right? And now we think about what happens. As we know from the first problem we did, because the current flowing through here is increasing, then the loop is going to have a current flowing through it that's going to point in the opposite direction, right? So there's going to be an induced current here that's going to flow around like this. Because if this is greater than 0, then that means that the direction of the induced current needs to be opposite to the direction of this current. So if that current's going around this way, the induced current has to go up like this, right? And of course we know that there's going to be an induced EMF in our external coil. And we know that that induced EMF is basically just equal to negative d phi dt. And since we have a solenoid, we know that our magnetic field is mu naught times the number of turns per unit length times the current, and then times the area here. We need to take the time derivative of this, but everything here, except for I, we can pull out. So mu naught NA, and then we would have a di dt here. This would be what our induced EMF would look like. And then we could, of course, talk about the induced current if we want to. The induced current is going to be equal to the induced EMF divided by whatever the resistance of the ring is. So that would be mu naught NA over R di dt. Okay, this isn't anything new. This is basically a repeat of the first problem that we did, deriving what the induced current in this situation is going to be. There is a negative sign here from Lenz's law. Okay, now you could ask a pretty reasonable question, which is, suppose that you are a positively charged particle sitting inside of here, and due to the changing flux of the solenoid, there's now an EMF out here. That EMF produces a current, and of course that means that there is going to be a force exerted on this object right here, right? And depending on how big the charge of the charge carrier is, Q, the size of the force is going to be proportional to the electric field. If there's a force there, and there needs to be a force in order to make the current actually move, there must actually be some kind of electric field there. So we're going to call this an induced electric field. An electric field that's been induced purely because the flux through this object is changing. Now, we can look at this from kind of like an end view, all right? If we look at it from the end, what we would see is if we were looking at it from here, right? We're looking in this direction here. What we would notice is that we have this loop right here with area A, right? And it would just be circular now. So that's our area A. And surrounding it, we have our larger circle, right? And we know that there is a magnetic field going into the page here from the solenoid. That's the magnetic field of the solenoid. We'll call it BSOL. And what we've said now is that, let's draw the direction of the current too, so that from this end, the current is going around this way, right? So that's our current I. The current in the outer ring needs to go the other way. So it's going to go this way. That's the induced current. And of course, I guess I could also put our ammeter up here too. So there's our ammeter. All right, so we have this end view now. The current flowing around like this. Okay. So what we're going to argue then is that not only is there an induced current there, but there is also a magnetic or an electric field. And we'll draw that like this. We're going to say that there's also going to have to be an electric field within the wire, which actually means that there's an electric field just in space in this location, right? I mean, even if there wasn't a wire here, there would presumably still be an electric field circulating around here. And how could we find what the size of that electric field is? Well, we know from here that the induced EMF is equal to this, but we also know another way of finding EMF, and that is by using this equation. EMF is also equal to the integral of E dot dl. This is basically our definition of what, of voltage. This was our original definition of voltage. So if we put these two equations together, we can write that the integral of E dot dl, which is EMF, should also be equal to the negative of the derivative of the flux. Like that. And that means that we can actually figure out what the size of the electric field here is. Okay, because if I tell you that the radius of this loop is r, I can now evaluate E dot dl around this loop, right? And in order to do that, I also have to define what my dl vectors are going to be. Dl vectors are going to be just little pieces of my loop here. And we can do E dot dl around the loop, and we'll find that dl and E are parallel everywhere, as long as we do the evaluation of this around this loop right here, right? And that's what we're going to do. We're going to go all the way around the loop. So we're going to do a path integral where we start and end at the same points, okay? And that means that on the left-hand side here, what we're going to get is just E times 2 pi r. And on the right-hand side, we'll get all of this junk. And so what I'm going to do is, just to talk about the size of the electric field, we're going to take the absolute value of this thing right here. So we're just going to write this as the absolute value of the rate of change of the flux. And then we'll solve this to say that the size of the electric field is just going to be equal to 1 over 2 pi r multiplied by the absolute value of the rate of change of flux. And this equation here is like a more complete version of Faraday's law. Right? It's still Faraday's law. But we get this answer here. In fact, we can look at the answer we have right here and say that in this particular case, the size of the magnetic field would be 1 over 2 pi r multiplied by mu naught times n times a times di dt. That's what you would get in this particular case. And we're going to do a problem right here. We're going to see how this works. But I suppose we could have talked about this at any point, but now that we're kind of effectively finishing up Faraday's law, it's worthwhile to think about the fact that what this says. Let's just look at what the equation says. It says a changing magnetic flux produces an electric field. And I think this is the first time we've seen an equation that technically has magnetic fields and electric fields in the same equation that doesn't involve... Like, we had this one equation that was like velocity is equal to E over V, right? But other than this, and this really came from relating forces, this is the first equation we have that truly relates electric fields and magnetic fields directly. And we can write it even more completely here, like this. Oops, not B. Integral of E dot dl is equal to, this is also an integral, it's negative d dt of this integral, and that is a more full statement of Faraday's law. A changing flux generates an EMF, but an EMF is E dot dl. So what I love about this equation is on the left-hand side you have electric field, on the right-hand side you have magnetic field. So there's a direct connection between these two objects. So if there was any doubt in your mind that the magnetic and electric fields are related to each other, this equation really kind of brings it home. Now I know that looking at an equation with a bunch of integrals and stuff in it doesn't really help very much, but that doesn't matter to me. For me, when I look at this, I just see E on one side and I see B on the other side. And I see that they're related by something very simple, which is a derivative. And yeah, there's some integrals that go on here, but the derivative part is what matters, right? What does this ddt tell us? It tells us that the only time you're going to generate an electric field from a magnetic field is when the magnetic field is changing in time. More specifically, it's the magnetic flux that's changing in time, right? But you can reinterpret that if you want to also mean that anytime the magnetic field is changing in time, you're going to generate an electric field, right? This is the core of electromagnetism expressed in this equation here. The idea that changing flux produces electric fields. Not just that changing flux produces an EMF, which is what Faraday's law says, but in fact, the change in flux really does produce an electric field. And that is a really powerful idea, which at its core is going to be used as a way to provide a mechanism for light to propagate, which is where all this is going, is because we want to prove that the phenomenon that we think of as light is actually just an electromagnetic phenomenon, and this is one piece of proving how light can propagate through a vacuum, just by fluctuations in these fields. Okay? All right, so eventually we're going to write a version of this equation down, probably by the end of today's class, where the B and the E are in different places. And that is where you're going to see like the complete like connection of how electric and magnetic fields can basically just kind of transform in and out of each other. Let's look at an example of a problem that we can solve like this. Oh, before we do the problem, it's worth noting in this case that normally in, say, a normal electric circuit, right? So let's just use a regular circuit. So let's say we have a circuit that has a resistor, and that's it. Just a battery, a resistor, and that's all. So EMF here, resistance here, and obviously there'll be some current flowing, right? All right. Now, if I pick a point, like right here, right? And I perform the operation of integral E dot dl, right? if I do E dot dl, and let's say that I go from the point A to the point B, then what am I going to get? Well, I'm going to get, I think, negative I times R, right? You all remember that from our the loop rules, right? When you go from A to B here, you're going through a resistor, and if your path is in the same direction as the current, you get a negative sign, right? And that tells me that negative IR then should be equal to, what does this give me? Well, it's basically just going to give me E times L. Okay, because the electric field in the system is going to point like this, and whatever the length between these 2 points here, E times L is going to be equal to this. Okay. Now, what if I do this, though? What if I start from point A, and I come back to point A? So I do this. What are we going to get here? So we start from point A, and we go all the way back around to point A. What am I going to get from this? Another way to ask that question is, what is the potential difference between point A and itself? Or if I were to take a multimeter and put one here and put another, it's 0, right? So you're going to get 0. So now compare that to this equation here. This equation tells us that E dot dl around a circular path, this path right here, is actually equal to something. So this type of electric field that's being produced right here is what's called a non-electrostatic electric field. Because for static electric fields, this is true. Any static electric field, it doesn't have to be the field of a loop like this. I could take a positive charge right here, and I could come to some point right here, and I could do a path around here, and I could ask the question, what's E dot dl equal to? And the answer would be 0 again. As long as you go around a closed path, you're still going to get 0. But not when you have a changing flux. So changing flux is going to produce what's called a non-electrostatic field, and we say this because this type of field, what does the field look like? I'll redraw it again down here. This is what the field looks like, right? In fact, these are what the field lines look like. They're circular. You have circular field lines, right? Those circular field lines all surrounding our little solenoid here. And the magnetic field's in, right? So you got a magnetic field here, and you've got your circulating electric field lines here. We call it a non-electrostatic field because there's no way that you can produce this just by some arrangement of electric charges. You can produce all sorts of interesting types of fields by manipulating, arranging electric charges, but this is one that you can't do that for. So we call it a non-electrostatic electric fields. Okay, let's do this problem now. All right, so within the green dashed circle shown in this figure, the magnetic field changes with time according to the expression B equal to 2t cubed 4t squared plus 0.8, where B is in Teslas, t is in seconds. And the radius r, which is this radius here, is 2.5 cm. It says when t is equal to 2 seconds, calculate A, the magnitude, and B, the direction of the force exerted on an electron placed at point P1, which is at a distance r1 equal to 5 centimeters from the center of the circular electric field region. And then we also want to find at what instant is this force equal to 0. All right, so first thing to do is to read it again, because I got lost. Within the green dashed circle, we have a magnetic field that's changing, okay? And the first thing we want to do is to calculate the magnitude and direction of the force exerted on an electron placed at point P1. Okay, so really what that means is we need to figure out what is the direction. Here's what we need to do. What is the size and direction of the electric fields at point P1. And to do that, we're going to have to use our equation from above, which is that the integral of E dot dl around a closed path should be equal to d dt of this. Okay? So let's go about doing that. All right. So the first thing I notice is that our magnetic field is changing in time, but does not seem to change in space. Meaning that the magnetic field is not a function of the radius or the distance away from the center. It just changes with time. So at a moment in time, the flux is some value, and then it changes from moment to moment. But the magnetic field does not change with respect to any spatial dimension, r, x, y, anything like that, right? So I'm pretty sure we can just change this to ddt of b integral dA, which is just going to be dB dt times the area, and the area is just going to be pi times r squared. Does that make sense? Now, in order to do the left-hand side of the equation, please let me know if you have any questions. I know this stuff can be very tricky. It all makes sense to me, but it doesn't mean that it makes sense to you. So if you get lost, please ask a question. Okay, we need a circular path. And we need it to be on P. So I'm going to try to draw a circle through P that is also centered. That looks kind of okay. I think it suffers from not truly being a circle, but that's fine. So this is going to be our path for this integral. God, I hate that it does that. If I try to write too small, there's all kinds of weird stuff. So over this circular path here, and we have a choice of how we're going to perform this. So what I'm going to ask you all to do is to imagine that this path is actually a circuit, like a wire, and tell me what the direction of the current through this wire would be at t equal to 2 seconds. And we'll use this to figure out the direction of the electric field, which we're going to use to figure out, oh, there's a minus sign here, by the way, too. Minus, minus, minus. Okay, so can you all figure that out for me? What direction would induce current in the path be? What do I need to know? What's the first thing you need to ask yourself when you're finding induced current? Is flux increasing or decreasing? Exactly. Exactly. Now we know the magnetic field points into the page. We can see that in the picture, right? How are we going to figure out if at t equal to 2 seconds the flux is increasing or decreasing? How can we figure that out? The expression, what do you mean? If we plug in values for t. Well, if we plug in values for t, it's going to tell us if the flux is... it'll tell us if the field... We need to see how it changes, exactly. We need to see how it changes. So in order to do that, if we really want to know if the flux is increasing or decreasing, wouldn't we just take the derivative? Take the derivative of B and determine if it's positive or negative, basically, right? That's what I would try to do. So that's basically what you're saying, right? Okay. So let's figure out what dB dt is real quick. So dB dt, very easy derivative to do because it's just a power rule. So it's going to be 3 times 2, so 6t squared, minus 2 times 4, so 8t. And then when we take the derivative, this term doesn't have a t on it, so nothing happens there. So now if we take the value of dB dt at 2 seconds, I don't know if that's a good way to write that or not, but this is going to be 6 times, 4 minus 8 times 2, so 24 minus 16, which is 8, I guess. So positive 8. So that means that if the field is increasing in time and the area is staying the same, then our flux is increasing. So if the flux is increasing, right, then that means we need to construct a current direction that produces an induced field opposite to all these x's here, which would be out, obviously. And I believe that that means that the current would have to be flowing like this. Okay. Now, is there any current there? No. It's just a path in empty space. But by figuring that out, we can then say, well, if I know that's the direction the induced current would be, that also tells me that at point P1, right here, that's going to be the direction of the induced electric fields. And down here, for example, the direction of the induced electric field would just also point tangent like this. Okay, so now that we know that, let us do our path integral here on the left-hand side. And the whole point of doing all that was to figure out what direction the path we're going to go. So we're going to go in the direction of positive current, which is going to make it so that E and dl are parallel, which means that this equation right here is going to reduce down to E times the integral of dl. E is going to be the same at all points on here because it's a symmetrical situation. Every point is the same distance away. Integral of dl is just going to be E times 2 pi r, like this. And now we can put everything together. So we have electric field is equal to, the pi's cancel. Looks like we basically just have 1 over 2r times dB dt. That's all that's left, right? And a negative sign. Now the negative sign isn't going to be particularly useful to us now because we already figured it out. So we're just going to absolute value both sides here just to get rid of our negative sign. And we're going to end up getting that the EMF, or the electric field, is basically equal to 1... Wait a minute. I left something out. There's an r squared in here. I knew that didn't look quite right. There we go. There we go. That looks more correct. The units look right, too. What are we supposed to do? We're supposed to figure out the direction of the force exerted on an electron located at point P1 and the magnitude. So to do that, we need to find the electric field. Let's find the electric field. So it's going to be negative big R, which is 2.5 centimeters, so 0.025 meters squared, divided by 2 times little r. Oh, which r are we using here? It's the radius of this path, so that should have been R1. R1? R1 is, I don't think we're using R2. R2 is for another problem, I think. R1 is equal to 5 centimeters. So we're dividing by 0.05 meters. And then multiplying by dB dt. We actually already calculated what this is equal to. At 2 seconds, dB dt was equal to 8, right? And that's going to be 8 Tesla per second. Assuming we didn't make any mistakes here. 6 times 4 is 24 minus 8 times 2 is 16. Seems like 8 to me. So we end up getting the size of our electric field, positive, because we got rid of the absolute value signs. So now we're going to get 0.025 squared divided by 2 divided by 0.05 times 8. I got 0.05 Definitely could have done this in our heads, but that's okay. 0.05, and then that's going to have units of newtons per coulomb or volts per meter, however you want to write it. But that's not our answer. That's just the direction of the electric, that's the size of the electric field. The question we had to answer was the direction of the force exerted on an electron. So now, if you have an electron right here, because it has a negative charge, so we have a little electron here, because it has a negative charge, the force that it feels is going to be opposite direction here, F. And we can say that the size of that force should be equal to the size of the electron charge multiplied by the electric field. So we do 1.6 times 10 to the minus 19 coulomb times the electric field of 0.05 Newton per coulomb, and we get an answer of 8 times 10 to the negative 21 newtons. And that's the size of the force. The direction is given from the picture above. Okay, any questions? No? Part C says, at what instance is this force equal to 0? So how do we figure that out? When is the force going to be 0? When the field is 0? I don't think that's quite right. The electric field, the magnetic field is never 0 if you look at it. If you look at the equation, right? No, that doesn't work. There's this constant term at the end, so the magnetic field's never 0. And it's not the magnetic field that matters anyway, it's the derivative that matters. So we want the derivative to be equal to 0 right here. So if we set that equal to 0, then we're going to get 6t squared minus 8t is equal to 0, which means that we can pull out a 2t, and we'll have 3t minus 4 is equal to 0, which means that at t equal to 0 or at t equal to 1.3 seconds. And that's the answer to part C. Anyone have any questions? If not, this is a great place to take a break. So we'll take a break until 3:26.